Welcome to this explainer. Today we're opening up our interactive digital notebook to explore something absolutely mind-blowing. We're going to look at the fundamental rules that literally orchestrate the mechanics of our entire solar system. I'm so incredibly excited to guide you through this, because we aren't just looking at some dry, abstract concepts today. No, we're uncovering the hidden, invisible tracks that guide every single planet, moon, and comet spinning through the void of space. Think back to the very first time you ever saw a model of the solar system. Maybe it was one of those plastic models in a science classroom or just a drawing in a textbook. Almost always, those models show the planets moving in these flawless, perfect rings around the sun. But here's the big question for you. Do planets really travel in perfect circles? Okay, let's dive into this, because the geometric reality of our universe is actually far more dynamic and, honestly, a whole lot more fascinating than those simple classroom models would have you believe. So here's our digital table of contents for today. We're going to build our mental model step by step. We'll start with the shape of the orbits in Law 1, then we'll add speed into the mix with Law 2, and finally, we'll wrap it all up with the math in Law 3. All right, kicking things off with Law 1, elliptical orbits, which is all about the actual shape of those planetary paths. Right here is the exact statement of Kepler's first law, also known as the law of orbits. It states that the orbit of a planet is an ellipse with the sun at one of the foci. So, right out of the gate, we are completely tossing out that idea of the perfect circle. Planets absolutely do not trace a perfectly round path. Instead, they travel along this stretched out, kind of flattened trajectory. To really wrap our heads around this, we need to look at the geometry of an ellipse. Basically, an ellipse is an elongated circular shape possessing two central focal points, which we call foci, labeled here as F1 and F2. Now, what's really interesting about this slide is how it fundamentally changes our view of the sun's position. Right? In a perfect circle, the sun would be sitting dead center. But in this elliptical shape, the sun isn't in the exact middle at all. It's firmly anchored at just one of these two glowing central focal points. And the other focal point? Well, it's literally just empty space. This means that during a planet's year, there are going to be times when it's significantly closer to the sun and times when it's much further away. Okay, let's move to and see how this builds into Section 2, Law 2, equal areas. This is where we upgrade our model by bringing speed and geometry into the mix. Kepler's second law, the law of equal areas, tells us that the line joining the planet and the sun sweeps equal areas in equal intervals of time. To help visualize this, I want you to picture a glowing, straight radial line. Think of it like a massive cosmic tether, connecting a moving planet directly back to the center of the sun. As the planet travels along its elliptical path, this glowing line sweeps through space, kind of acting like a giant windshield wiper, just coloring in a huge section of the solar system. Let's compare two totally different parts of the planet's journey. Imagine a planet traveling from point A to point B over the course of, say, exactly 1 month. That glowing radial line sweeps out a specific wedge-shaped area. We'll call that Area 1. Now imagine that exact same planet later in its orbit, traveling from point C to point D, again over that exact same duration of 1 month. The line sweeps out another wedge, Area 2. Even though the planet is at a completely different distance from the sun, Kepler discovered something honestly magical here. He found that if the time intervals are identical, the geometric sectors swept by those radial lines are mathematically perfect equals. Area 1 is exactly 100% equal to Area 2. So, what does this actually mean for the planet's movement in real life? Well, the crucial point is this. Because the sun is at one focus of the ellipse, the distance the planet travels near the sun from A to B makes a short, wide, and really fat wedge. To sweep out that massive area in just 1 month, the planet must physically travel much faster along its orbital path. It is literally whipping around the sun. Conversely, when you look at the planet when it's much farther away from the sun, moving from C to D, that wedge is very long and super skinny. To keep the area perfectly equal, the planet covers way less distance along the curve. It moves much slower, just lazily drifting through the outer edges of its orbit. The beautiful outcome of this constantly shifting speed is that the swept areas remain perfectly, flawlessly uniform. All right, bringing us to Section 3, Law 3, the period equation. And don't worry, we aren't doing a textbook chore here. Think of this math more like a sleek, futuristic targeting computer locking onto a universal truth.
Behold the law of periods. T squared is directly proportional to r cubed. Kepler realized that the time it takes a planet to orbit the sun is directly, undeniably tied to how far away it is. Specifically, the square of the period of revolution of a planet is directly proportional to the cube of its mean distance from the sun.
Let's break down exactly what these variables stand for on our digital UI, so this whole mathematical relationship becomes immediately accessible and super easy to grasp. T stands for the time period of revolution. Simply put, this is the time it takes for the planet to complete one full orbit around the sun, what you and I would just call one planetary year. R represents the mean, or average radius distance from the planet to the sun. Now, because we know the orbit is an ellipse from Law 1, the distance is constantly changing, right? And that is exactly why we use the average distance here. When you take that proportionality and turn it into a hard, concrete equation, you get this. T squared divided by r cubed equals a constant, which we label as k. This is absolutely staggering when you think about it. If you take the time it takes Jupiter to orbit the sun, square it, and divide it by Jupiter's average distance cubed, you get a specific number. If you do the exact same math for Mars, or Earth, or Venus, no way, right? Yes way. You get that exact same number. It perfectly resolves into this universal constant, locking the rhythm of every single planet into an unbreakable mathematical code. And this brilliantly illustrates exactly what we call the universal choreography. It really brings everything we've talked about together. We've totally upgraded our understanding today. We moved from assuming planets just roll on simple circular tracks to understanding the elegant, stretched ellipses of the first law. We discovered the dynamic, shifting speeds of the second law that keep the celestial geometry in perfect balance. And finally, we uncovered the constant mathematical reality of the third law that completely unifies the entire system. As we close out our digital notebook for this explainer, I want to leave you with one final provocative thought. How do these three geometric laws silently dictate the motion of every single celestial body in the universe? Because, these aren't just historical footnotes or some abstract theories on a screen. Right now, at this very second, these exact geometric principles are the literal active mechanisms keeping our own planet safely in orbit. They govern the satellites providing your GPS, the moon pulling our tides, and even the most distant exoplanets orbiting alien stars. They are the silent, beautiful rules of the cosmic dance. Thank you so much for exploring them with me today. Keep looking up and keep questioning the mechanics of the amazing world.